said was that any continuous function on the interval could be uniformly approximated by a polynomial. Well, there are various other functions that we regard as nice functions that you'd like to be able to approximate by. And so last time I defined what an algebra is, and we'll also need some closely related thing. So let's make another definition. A subset L of continuous functions. They don't have to be continuous, but this is the only context where we're going to look at it. So a subset L of the continuous functions on a compact metric space. Again, that's the only context that we're going to look at. It could be just any underlying set. It's called a lattice if the following is true. Two functions f and g in L implies that the max of f and g, which is written this way, f of g is in L, and for any two functions in L, we can take the minimum of the two functions and that is also in L.
Now is that you take a point x and then the maximum of f in g of x is what that function is defined as?
Yes, I'm not saying that one of f or g is bigger. You do it pointwise. So you look at a point, either f of x is greater than or equal to g of x or the other way around, and you take the largest value, or the common value if they're equal. So what are examples of lattices? Well, continuous functions on AB certainly are, because when you take the maximum of two functions, you can write a formula for it. The max of f and g at a point x is f of x plus g of x plus the absolute value of the difference divided by 2. Why is this true? Well, at a point where f of x is the larger, this absolute value goes away. This difference is f of x minus g of x, and the g cancels. When g is the larger, this gets switched, and this becomes g of x minus f of x. The f of x cancels, and we get g of x. And then when you do the min of two functions, you have the formula f of x plus g of x minus the absolute value of f of x minus g of x over 2. this way, that you can see that if you plug two continuous functions into this, out comes another continuous function. Same here. What's another example of a lattice? For example, the continuous functions on AB satisfying that it's 0 at the endpoint. And you just have to check the max of two such things. Well, it's another continuous function, and if you plug in x is equal to a here, you will get 0, 0, and the absolute value is 0 minus 0. So it will also satisfy vanishing at the endpoint. What's an example of something that's not a lattice? The polynomials are not a lattice. If they were, so on -1, 1, say, what is the maximum of the value x and negative x? Well, when x is positive, x is the bigger of the two. When x is negative, negative x is the bigger of the two. And so what you get is the absolute value of x, which is not polynomial. So some subsets are lattices and some are not. However, there's a close connection between lattices and algebras. I think my numbering system may have got off a little bit. I think this should be 2.9. What was the last number we had? Was it 2.8?
Yes.
Okay, thanks. So let XD be a compact metric space. formulas for the max and min. All we have to do is show, since we have an algebra, f plus g is in there, f minus g is in there, so we just have to show that the absolute value of any function in the closure is again in the closure. So it is enough to show that for a function h in the closure of A, the absolute value of h is in the closure of A. Now, since h is continuous, on a compact space X, its range lies in some bounded interval A to B. So what we're going to do is we're going to use the Weierstrass theorem on this interval. So by the Weierstrass theorem, there is a sequence of polynomials I'll use a different letter, Pn of t, converging uniformly to the absolute value of t on the interval A to B. By enlarging the interval, which won't harm anything, we can assume that 0 is in the interval AB. If it wasn't, then the absolute value of t would either be t if the interval's on one side of 0 or negative t if it's on the other. So if I plug in 0, Pn of 0 converges to 0. See, I don't really know anything about these polynomials. It could well have a constant term, which I don't want to have. And so we'll get rid of it. Pn of t's are converging to the absolute value of t, and the Pn of zeros are going to 0, as Qn of 0 equal to 0, and Qn of t goes uniformly to the absolute value of t on AB. So it's a minor adjustment. For reasons you'll see in a moment, I do not want a constant term on this polynomial. Okay, so what can we conclude now? If we put t equal to h of x, which is allowable because the values of h are all in the interval from a to b, so it makes sense to make this substitution. What do we get? We get that Qn h of x converges uniformly to the absolute value of h of x for x in our compact metric space. Now, what is Qn h of x? If a particular Qn of t, since it has a zero constant term, it can be written like this. Alpha sub 1 t plus alpha sub 2 t squared plus alpha sub k t of k. It's a polynomial whose value at 0 is 0. Then Qn of h of x, when I plug that in, it's alpha 1 h of x plus alpha 2 h of x squared, and so on. And the point is that this is in the algebra A bar. Now, I don't necessarily know that I have the constants in my algebra, and that's why I had to get rid of the constant term, so that I could see this is just a combination of h squared, and so on, up to some power h to the k. So that is in the algebra. Since A bar is closed, what we get is absolute value of h of x is in A bar. As I remarked at the beginning, to show that the max and the min are in the algebra, it was enough to show that we can take absolute values and stay inside A bar. So you may have an algebra of functions like the polynomials that's not a lattice, but you're close to being a lattice. You just have to go to the closure, and then everything works nicely. So therefore, all f So we're now going to do what's called the Stone-Weierstrass theorem. So the original Weierstrass theorem we've already done, and it referred to density of polynomials in the continuous functions on any closed interval. The generalization in the Stone replaces the interval by a compact metric space. And indeed, if you know what a compact topological space is, which we haven't discussed, but if you happen to know it independently, then it works perfectly well there also. And what it seeks to do is replace the polynomials, which no longer make sense on a compact metric space, by an algebra of functions satisfying certain conditions, which will allow us to conclude that the closure is C of x. So there are several forms. For an algebra on x. And I'm sure I couldn't list them all, because if I listed them all, you would be able to find another one that read slightly differently. But here are some of the main ones. So there are two basic questions. The first of these is what conditions imply that a bar is equal to continuous functions on x. Secondly, given an algebra A, can we conveniently describe the functions in the closure? So these are the two issues. Generally, of course, you would like the closure to be all continuous functions, but you don't always get that information. So I'll get to the answers for this in a moment, but let's just look at an example. Sometimes you can use the existing theorems plus a few tricks to deduce new situations. So here's an example of this. So the algebra is equal to the set of polynomials on 0, 1, with the property that when you evaluate at 0, you get 0. What is the closure? Well, it's pretty clearly not all continuous functions, because I'm only looking at polynomials that vanish at the left-hand endpoint. And so anything you can reach by a sequence of such things will also vanish at the endpoint. So continuous f with the property that f of 0 is equal to 0. So assuming that we can have a nice description of A bar, that probably has to be it, because there aren't any other reasonable candidates around. So, in fact, we have equality. So let's see why that is. Example rather than a theorem. I'm not going to give full details in the proof, but I think I'll do enough to convince you that it's true. So how does one proceed? Take a function f in C of 0, 1 with f of 0 is equal to 0. I would like to approximate that closely with a polynomial that vanishes at 0, so no constant term. Now there's an easy way of doing it and a hard way of doing it, but both have their merits, so I'll do both. So method 1, by Weierstrass, there exists a sequence of polynomials Pn of x Pn of x goes uniformly to f on 0, 1. Since f is vanishing at 0, that says that when I evaluate the polynomials at 0, they tend to 0. Therefore, Pn of 0 goes to 0. So the constant terms, if there are constant terms on these polynomials, are tending to 0. So we can subtract them off. Let Qn of x be equal to Pn of x minus Pn of 0. So what that does is it makes it into a polynomial with no constant term. Qn of 0 is 0, and we also have that Qn of 0 goes uniformly to f. Qn of x. And so that does it. We've approximated the given function using polynomials that vanish at 0. Now the other technique, having seen that one, you wouldn't necessarily do this one, but it has its uses in other contexts. So I want to basically show you the tricks that one can bring to bear. Okay, so f of 0 is equal to 0. Which means that the function, whatever it does, must end up at 0. So there's a typical typical f that vanishes at the origin. Now what I will do is I will adjust it so that it's 0 on a little interval here. So for a given epsilon, adjust f to a function g, all I'm going to do is change it close to the origin, and instead of just vanishing at 0, it's going to vanish on some small interval, and then when it rejoins the curve, this will be g. So the only difference between f and g is in a very small interval close to the origin, where f was small anyway, and I make it 0, and then I draw a straight line segment and back up to the curve, and then continue with what I had before. And so I can arrange this as long as I only make the adjustment in this range. You can see that the infinity norm of f minus g can be made small. Now the purpose of doing that, normally I can't take a function and divide by x and expect to have a continuous function. But in this case, I can, because dividing by x is only a problem at the origin, and this function is uniformly 0 for a while. So there is a continuous function h of x, so that h times h of x is equal to g of x. And that's possible purely because I have the function g vanishing on an interval that contains 0. So then the h I can approximate by polynomials. Take Pn of x going uniformly to h of x, and then x times Pn of x goes uniformly to g of x. And now I've got a function, when I plug in 0, I get 0 because of the x here. So these uniformly approximate g, which was uniformly approximating f. So a triangle inequality says that one of these is close to the original. So the infinity norm of f of x minus x Pn of x will be less than epsilon for n sufficiently large. answers. So again, it's of necessity a partial list. So number 1, that was the question, what conditions imply that you get all continuous functions? So the standard one is this. A bar equals all continuous functions is implied by the conditions. First of all, the constants are in A, and A separates points. I'll explain what this is in a moment. In other words, if x1 is not equal to x2 in x, then there is a function f in A such that the value at x1 is not equal to the value at x2. So if you ask most people to state what the Stone-Weierstrass theorem is, this is what they would give you. This is the standard form. But it's not the only form. Or, here's another set of conditions that give you the same conclusion. And this is called the two-point condition. Given an f in C of x, 2 points x1 not equal to x2 in x, and an epsilon greater than 0, there exists a g in our algebra of functions so that at the 2 points g of x1 minus f of x1 is less than epsilon, and g of x2 minus f of x2 is also less than epsilon. This is sufficient to imply the closure of the algebra is all continuous functions on x. So the picture that goes along with this so here's f. Here are 2 points, x1 and x2. And then we just have to be able to find a g in the algebra that closely approximates the function just at those 2 points. So G and A, the dotted line, I've deliberately drawn it so it's far away from F most of the time, but it comes very close at x1 and x2. So it's really quite a weak requirement, but nevertheless it is sufficient to be able to prove that the closure is equal to C of x. And now what about question number 2? If you're given an algebra of functions, how can you characterize what the closure is? I think the nicest answer to that is as follows. A bar is the set of continuous functions with the following property. F satisfies the two-point condition for A. So it's those functions where you can pick any pair of points and get something from the algebra very close to F at those 2 points. And that's usually enough to be able to tell whether a given function is in the algebra or not. So, almost out of time, but let's go back and look at the classical situation of polynomials inside continuous functions on 0, 1. So, A contains constants because the constant functions are polynomials. And what about separating points? Well, in this case, we have one polynomial that will do the job. So P of x equals x separates points in 0, 1. Given any 2 points, plug them into this polynomial and you get 2 different answers. So that was one version of the Stone-Weierstrass theorem. Containing the constants and separating points, we will see is sufficient to get that the closure of the algebra is the set of all continuous functions. What about this 2-point condition? Well, the 2-point condition can be satisfied by a linear polynomial mx plus b. Graphically, it looks like this. Here's a continuous function f, and I want to show that the 2-point condition holds. So for any choice of 2 points, I want a polynomial close to f at those 2 points, we actually get it exactly. And it's nice because we only have to worry about 2 points at a time. So both forms that I have described would be good enough to determine that the closure of the polynomials is the whole of the continuous functions on 0, 1. Okay, so we're out of time for today.